Okay, now we're going to talk about the Schrodinger equation, and I apologize the background noise. I'm actually in the airport. So,
May I
the
have your attention, please?
Schrodinger
Delta
equation
Airlines paging passenger
is the
Robinsons.
equation
Please
that
report to gauge
describes the
Delta
wave function,
78 for City Delta
and the simplest way
representative
we
boarding
write it
both messages.
is here. We have h psi equals e psi, and notice that this thing h, whatever the heck that is, has a funny hat on top. So that's pretty abstract. I wonder what we mean by this. But okay, in the last section, we worked on answering the question, basically, where are you? And that was the Born interpretation. So where are you? The probability distribution, at least, of where you might be, turns out to be the wave function, the magnitude of the wave function squared. So p of x equals the absolute value psi of x squared. Okay. Well, now what we're doing with the Schrodinger equation is we're asking a different question. How much energy does the wave function, does the object have? And the energy in general is given by kinetic energy, how much energy is associated with motion, and then the potential energy. In the case of gravity, that's how high up you are, but there's lots of different potentials that we'll talk about over the course of the term. Now, before we get to solving the Schrodinger equation, there's a few constraints, what we might call boundary conditions, on this wave function psi. And the one that really matters at the moment is that the wave function has to be what we call single-valued and continuous. And you can think of this as being related to the probability distribution. If you have a wave function psi that looks like this, it's some curvy thing, and then at some point it leaps up and has a totally different value and is curvy again. If you think about the probability distribution there, we square that function. It's going to look maybe like this. And then there's some point here that I've circled in red where the probability of finding the object has two different values. And that's just dumb. There's no real, it doesn't really make any sense. And so we're not going to let that happen. Because it doesn't make sense, we're going to say that the actual wave function has to always just have one value and move continuously from one value to the next as we move around. Now, as I've written it for you so far, this function h psi of x equals e psi of x might be nice and concise for a mathematician, but what the heck does it mean? So let's start to break this down. This thing h is actually minus h bar squared, remember that's Planck's constant squared, divided by twice the mass, times the second derivative of the wave function, plus a potential v of x times the wave function, is equal to, again, energy times the wave function. So the second derivative times the wave function is telling us something about kinetic energy. The potential energy times the wave function is telling us something about potential energy. And then energy times the wave function is telling us something about the total energy. This is wave function out in the way. So we got kinetic energy, which is a function of position, times potential energy, which can be a function of position, is equal to the total energy. That's all it is. The Schrodinger equation is fundamentally an energy balance. And the total energy is a conserved quantity. So that's an incredibly important thing. The total energy of a system doesn't change with position. So it's what we call a conserved quantity in physics. Okay, let's start to break this down a little bit more. We've got this expression minus h bar squared divided by twice mass times the second derivative of the wave function. This means literally, first of all, take the second derivative of the wave function psi of x, then multiply by Planck's constant divided by 2 pi squared, then divide by twice the mass, and then change the sign of the whole thing. That's pretty straightforward. So this whole thing, minus h bar squared over twice mass times the second derivative of the wave, or the second derivative, is itself an operator. We call it t hat, and that thing is the kinetic energy operator. Okay? So that is telling us something about kinetic energy. Okay, well the next thing we have is this thing that we call the potential energy. So what's that? We call it v of x. It's definitely a function of x. It's also really an operator, though we don't actually put a hat on it, because in this case it just means multiply a function by some other function, So we just call it V of x, nonetheless. And from classical physics, the potential energy actually gives you the force that's acting on something. So the force is equal to the negative of the derivative of the potential. So the potential's steep, it means there's a strong force, and if it's steep up to the left, it means you're pushing to the right, and if it's steep up to the right, it means you're pushing to the left. Okay? So this potential term is incredibly important, because really, in the end, V of x tells us how the outside world, how everything else, is interacting with and acting on this object, this particle, this what we call system that we're interested in describing with the Schrodinger equation here. So you get a particle, you get an atom, you get a molecule, whatever it is. That's the system that we're trying to describe. And that potential V of x, as we'll see, completely and totally defines the problem. So every single example we'll go through this semester is fundamentally characterized by a different type and value of the potential energy function. So every time we define a new potential energy function, we're going to be talking about a new kind of system. So keep in mind that very, very tight relationship. Let's give an example. Maybe one of the more simple cases of a potential, we could think about a skateboarding system. So let's think about skateboarding on the half pipe, or snowboarding on the half pipe. So here's a half pipe. It's kind of curved, goes up pretty steep on the edges. The y value of this system is going to be energy. So potential energy in this case is what we're interested in, but y is energy. And then we have a single dimension x. We're not going down the pipe, we're just going back and forth. So this curve here is the potential energy. In the case of gravity, you can think of it literally as the ground at the half pipe. Okay? And then the total energy of the system, because energy is constant, that has to be a flat horizontal line in this system. So the energy is going to be a flat line. The potential energy is going to be a curve there. And the point where these two intersect, that's circled in green here, is extremely important. That's basically the top of the arc of what's his name, the flying tomato, as he's going up and down across the half pipe. Sean something, right? And so we're going back and forth and back and forth and back and forth. And we're basically rolling back and forth by this green curve. So at those two limits circled in red, that's where the tomato stops, up in the air. And so we call those classical turning points. You should watch out about that term classical, because we're talking about quantum mechanics. But in a classical system, at least, that's where you turn. The other thing, the other part of this equation here, then is the difference between that total energy and the potential energy. And that's the kinetic energy. And that's actually at a maximum here, right at the bottom of the half pipe, where the difference between the total energy and the potential is the greatest. So when you're down at the bottom of the pipe there, you're moving as fast as you're ever going to move.